Integral as a net change, AP questions. Objectives. By the end of this lesson, you should be able to set up and solve AP net change problems, find and store functions and points of intersection in the graphing calculator, and evaluate integrals involved in net change problems on the graphing calculator. Alright, let's jump into our first AP question. Traffic flow is defined as the rate at which cars pass through an intersection, measured in cars per minute. The traffic flow at a particular intersection is modeled by the function f, defined by f of t equals 82 plus 4 sine of t divided by 2 for times t between 0 and 30. And f of t is measured in cars per minute, and t is measured in minutes. So before we look at the 4 parts of the question we're being asked to answer, let's try to understand this function that I've been given. This function that I've been given represents a rate. It represents a derivative. Even though this notation doesn't have the prime notation or d something dt, this is still a rate of change because of the units of measure are in cars per minute. So if I were to substitute a time, t, in minutes into this t, or into this t in other words, what units would come out are in cars per minute. So just substituting in something like 1 right here, f of 1. So I'd substitute a 1 right here into this t. So 82 plus 4 sine of 1/2 is a numerical value. That numerical value is in cars per minute. So it means that at exactly 1 minute, there are that number of cars per minute passing through that specific intersection, so a particular intersection. So just substituting in values into this t will give me out units in cars per minute. So now let's take a look at the first question. To the nearest whole number, how many cars pass through the intersection over the 30-minute period? So let's go again. To the nearest whole number, how many cars? So my answer has to be in a unit of cars. How many cars pass through the intersection over the entire 30-minute period? So the first thing I want to clarify is we are not just substituting in the number I see here, 30, into the function. So the best way to answer a lot of these questions is to truly understand the units. If I were to just substitute 30 into f of t, my answer would be in cars per minute. But we just agreed I want to know how many cars. So that means that in calculus we have two options. We're either going to take the derivative or we're going to evaluate an integral. Now in this case, I want to evaluate an integral. I want to get to just cars. If I were to take a derivative in cars per minute, my answer would be cars per minute, or cars per minute squared if I took the derivative of f of t. But instead, I'm going to evaluate an integral. Now, again, to help us understand the concept of units, let's say we were to graph this function f of t. So for now, let's assume I don't know exactly what it looks like. This is just my function f of t. Now, the units of my function, which means the units on the vertical axis we've said a couple times now, are cars per minute, and the units of my horizontal axis, time, is in minutes. So finding the area under the curve during the first 30 minutes, so from 0 to 30, the area is going to be the units of the base times the units of the height. So cars per minute times minutes, cars per minute times minutes, well, the units that are going to cancel are minutes, and my answer will be in cars. So understanding the units is really going to help us evaluate this first part of the problem. So part A, I'm going to have to set up the integral from t equals 0 to t equals 30. So I wanted to know how many cars pass through over the 30-minute period. So starting at time 0, ending at time 30, of the function f of t dt. Now, since the function has been given to us in the problem, 82 plus 4 sine of t over 2, there's no need to rewrite it. So we're talking about AP problems now, and we want to save ourselves some time. What we do have to write down is the setup of the integral. So this right here is absolutely required. So the integral from 0 to 30 of big F of t dt. So let's talk about a couple things now. I want to make sure that I write big F of t dt. So I don't want to start changing things to little f. There is no little f. There is no x's involved. So I want to be sure to recall the function that is being used in the problem. And now I need the numerical answer. So to find the numerical answer, this particular problem is a graphing calculator problem. So off to the left here you see a TI-84 graphing calculator. So let's go ahead and go over how we would enter this into our graphing calculator. Now, this one function is going to be used throughout the entire problem. We're probably going to have to use it more than once in our calculator. So we're going to go ahead and store it and enter it as y equals. So we can go ahead and turn the calculator on, go to y equals, and enter our function. And you'll see I've already gone ahead and done that. So 82 plus 4 sine of course, x over 2, because we don't have the variable t, but x will do. So here is my function. Now, something else we should troubleshoot right now is that we want to make sure that our calculator is in radian mode. So clicking mode, it is highlighted as radian mode because that will completely make our answer wrong otherwise. So y1 is right there in our calculator. So let's go back to the home screen. So second quit. And now we're evaluating this integral here. So we're going to go ahead and go to math, and we go to math 9. And our lower limit of integration is 0. Our upper limit of integration is 30. And to avoid entering that function and over again, we stored it as y1. So we're going to go to vars, go right 1 to y vars. We can hit 1 or enter for function, and then enter again for y1. And then we'll fill in the variable in our differential as an x. And then we can go ahead and hit enter. So the numerical answer is 2,474, and it says to the nearest whole number. So if this was not here, we would definitely go to the thousandths place, but because to the nearest whole number, our answer is 2,474 cars. So we wouldn't want to think of a fraction of a car. So let's go ahead and fill in our answer. So 2,474 cars is our numerical answer. So this is what we would need to write in order to obtain full credit on this problem. We'd have to set up the integral, but again, there's no need to write out the whole function. So 82 plus 4 sine t over 2, we can just call it what it was named, big F of t. And then we do have to write our numerical answer. And again, we were told to the nearest whole number, so no need to round or truncate to the thousandths place. Alright, so now let's move on to part B. Part B is asking, is the traffic flow increasing or decreasing at time t equals 7? Give a reason for your answer. So here is the traffic flow. Well, traffic flow had a name or a function. The function is called f of t. So here they've written it out in words. Is the traffic flow increasing or decreasing? But traffic flow is really can be thought of as f of t. So this problem is asking us, is the function, is f of t increasing or decreasing at time t equals 7? So now this takes us back to remembering that a function is increasing when its derivative is positive. So we're looking at the specific value right here at t equals 7. So for part B, we need to determine the sign, positive or negative, of f prime of 7. So is the traffic flow, which was called the function f of t, is f of t increasing or decreasing at time 7? We're really asking ourselves, is the derivative positive or negative at time t equals 7? And because this is a graphing calculator problem again, we can do this on the calculator, and we've already stored the function big F as y1. So now we're doing a derivative, a numerical derivative. We can go to math 8, and our variable is x, and we want to go to vars over to y vars, enter, and use y1 again. And we're evaluating this particular function at a specific value at 7. So since the answer is negative 1.7829, we know that f prime of 7 is a negative value, so if the derivative is negative at a particular value, the original function is decreasing. So we can say f prime of 7 equals negative 1.872, which is less than 0. So there is my reason. So f is decreasing. Or we could replace f with traffic flow, as that is what the function f represented, and that was the way that the problem was worded. So we'd probably want to put, so the traffic flow is decreasing. So we answered parts A and B of this question, and we'll hold off in a later lesson to go over parts C and D. Alright, let's jump into another AP question. Water is pumped into an underground tank at a constant rate of 8 gallons per minute. Water leaks out of the tank at a rate of radical t plus 1 gallons per minute for times t between 0 and 120 minutes. At time 0, the tank contains 30 gallons of water. So this last sentence meaning at the beginning, the tank already had 30 gallons of water in it. So let's go back and try to visualize what's happening. We have this underground tank that water is being pumped into constantly at this rate of 8 gallons per minute. So what I've just been given here is a function. So I'm going to go ahead and call it f of t. So the variable is t, and it's a constant function. So f of t is 8, and the units are gallons per minute. So in other words, it doesn't matter what time I plug in here. If I plug in the number 1, I still get 8 gallons per minute. So what that means is after 1 minute has passed, water is still pouring in at this constant rate of 8 gallons per minute. After 30 minutes have passed, it doesn't matter. Water is still pouring in at a steady rate. So imagine a faucet. So let's try to, again, visualize what's happening here. So let's say I have this tank, and I don't know, here's a faucet, and we have water coming in. So water is just constantly coming in at this rate of 8 gallons every single minute. And at the same time, water leaks out of the tank at a rate of radical t plus 1 gallons per minute. So that's a separate function. I'm going to call g of t, the other function, radical t plus 1, also in gallons per minute. So at the same time water's coming in, water's also leaking out. So let's imagine that there's a hole in the tank that's, I don't know, since it's not coming out at the same rate, maybe that hole is expanding. So water's coming out at different rates every single minute. So after 1 minute has passed, water is coming out at a rate of radical 2, because 1 plus 1 is 2, so radical 2. But after 10 minutes has passed, water's coming out at a rate of radical 11 now, because 10 plus 1 is 11. So let's say that hole in the bottom is expanding as time goes on. So that's why more and more water is leaking out, but the faucet that's pouring it in, nothing's wrong with that, so it's coming out at a constant rate every time. And at the very beginning, there was already 30 gallons in the tank. So let's say it already had some water inside of it. So now hopefully we have a good understanding of what's going on. So now let's try to answer the question. Let's start with part A. How many gallons of water leak out of the tank from time t equals 0 to t equals 3 minutes? Alright, so for part A, I'm being asked specifically about how many gallons leak out of the tank. So f of t was the going in function. So let me go ahead and label these. F of t was the water pouring in, and g of t was the water coming out. So just so we remember that. So for this first part of the problem, I'm only being asked to consider the function g of t, because g of t is the water pouring out, or the water leaking out function. So I'm not concerning myself with f of t at all. Nor am I concerning myself with this quantity that at time 0 there was 30 gallons in the tank. We're not being asked anything about that fact. I just want to know how many gallons of water leak out of the tank between 0 and 3 minutes. So I have two times here. I have t equals 0 and t equals 3, and those are going to be the limits of integration because I need to set up an integral for part A. For part A, I'm setting up the integral from t equals 0 to t equals 3 of my water coming out function, which is radical t plus 1 dt. So how do we know to set up an integral and maybe not find a derivative? Or maybe just substitute in these values, 0 and 3, into the function? Well, the answer is because of units. So if I were to just substitute, let's say 0 and 3, or let's just take 3, into this g of t function, plugging in a 3 here for this t and into this t, my units would be in gallons per minute. So I'd get 3 plus 1 underneath the radical, so 2 gallons per minute. But looking back at the problem, I wanted to know how many gallons of water leak out. So again, taking a derivative, the units wouldn't be correct. If I took a derivative of g, I'd get gallons per minute squared. So I need to integrate, and again, if you need to go back to this, that's fine. So g of t is some function, and the units of g of t on the vertical axis are in gallons per minute. The units on the t-axis are in minutes, so finding area under the curve, which represents a definite integral, the area of the base would be minutes, the area of the height would be gallons per minute, so gallons per minute times minutes, the minutes cancel, and we end up with just gallons. So that's how we know we're setting up an integral. So this particular integral is not a graphing calculator problem. In fact, it can be solved using U substitution. So this is a non-calculator problem all in general. So no parts of this problem are graphing calculator on the AP exam. So in our U substitution, we would let U be t plus 1. So du is dt. And our limits of integration would change because this is a definite integral. So if I substitute in 0, u of 0 is 0 plus 1, so that's 0. So my new limit would be u equals 1. And then u of 3 would become 3 plus 1, so that would give me 4. So my u equals 4. And t plus 1 becomes u. And dt becomes du. So now I don't have to care at all about this integral. I'm solving this definite integral here. So this definite integral, I'll drop the u's and the limits, goes from 1 to 4 of u to the 1/2 du. So now I find the antiderivative of u to the 1/2, so u to the 3/2 times 2/3, and then I substitute in 1 and 4. So if I substitute in 4, I get 2/3, 4 to the 3/2, minus 2/3, 1 to the 3/2. And now let's look back at the problem. How many gallons of water leak out of the tank between 0 and 3 minutes? This right here, as ugly and messy as it is a numerical answer. So we can stop right there and say this many, whatever this exact number is, gallons, leaks out of the tank between 0 and 3 minutes. So we should stop here at the risk of simplifying incorrectly and then losing points. We should stop here and box in our answer. So this many gallons leaks out of the tank between 0 and 3 minutes. So this is the soonest I can stop. I cannot stop right here at this step because my answer is not a number yet. But once I substitute in my limits of integration, I can go ahead and stop and say this is the answer. Alright, let's move on to part B. How many gallons of water are in the tank at time t equals 3 minutes? Alright, so this question, how many gallons of water are in the tank at time t equals 3 minutes? So this one is sort of a tricky one. Well, at the start, there were 30 gallons of water in the tank. So now we have to take that into consideration because we want to know how many gallons are in the tank at 3 minutes, and that depends on how many there were to begin with. So for part B, we're going to go ahead and start with the fact that there were 30 gallons in the tank to begin with. But then I have to consider, well, how many gallons have entered the tank during that time frame of the first 3 minutes? And then I have to think about, well, how many gallons leaked out of the tank during the first 3 minutes to figure out the total number of gallons that were in the tank at 3 minutes. So how many we had to begin with, 30, and then I need to add how many entered the tank between 0 and 3 minutes, and then I'm going to need to subtract how many leaked out of the tank during the first 3 minutes. So just to write ourselves some notes, I mean, we wouldn't have to write this on the AP exam. So to begin with, and then how many went in, and then how many gallons went out or leaked out. That's ultimately the setup that we're going to need to figure out. So how many gallons went in between 0 and 3 minutes, and then how many gallons went out between 0 and 3 minutes. Now, hopefully you're thinking, well, I know how many leaked out. I already found that in part A. And that's true. We absolutely did already find that numerical answer. So we can just copy that numerical answer from the previous problem. So that's eventually what we're going to fill in here. So now it's just a matter of figuring out how many went in. So the going in function was f of t. And so we can do the same setup to figure out how many went in. So I'm going to go ahead and put that off to the side. I can find the integral from t equals 0 to t equals 3 of the function, the going in function, 8 dt. So the antiderivative of 8 is 8t from 0 to 3. And then we'd substitute in 3, so 8 times 3 minus 8 times 0 is exactly 24. So 24 gallons went into the tank during the first 3 minutes. And maybe some of you were thinking, well, I didn't really have to evaluate this integral. If this is just a constant, well, after 1 minute has passed, 8 gallons poured in, if this is in gallons per minute, and after 2 minutes have passed, well then 8 times 2, 16 gallons must be in there. So after 3 gallons have passed, or 3 minutes have passed, there must be 8 times 3, so 24 gallons in there after 3 minutes have passed. So if you could have understood that based on the fact that the water coming in was constant, you didn't have to show this work for the integral. But setting up this integral is perfectly fine. And definitely shows a conceptual understanding. So for the numerical answer, we would want to go ahead and take 24, over, so this is how many went in, minus how many leaked out, so we would take our previous answer. And if we're not going to simplify it, we want to make sure and keep it inside parentheses, because since we're subtracting it, that's definitely going to make a difference. So it was 2/3 4 to the 3/2 minus 2/3 1 to the 3/2. So again, this is a numerical answer, so we can leave our answer like this. So there was 30 plus 24, and then minus however many leaked out. So the amount we started with plus how much went in minus how much came out. So that is our answer to part B. Alright, so now moving on to part C. Write an expression for A of t, the total number of gallons of water in the tank at time t. So part C is asking us to generalize what we did in part B. Part B asked us to find specifically how many gallons were in the tank after 3 minutes. But part C is asking us to write an expression for A of t, the total number of gallons in the tank at some generic time t. So let's go ahead and start. Part C is going to be A of t is going to have to equal, so we're about to write out a function. And writing out part B like this should help us write the function A of t. So to find the total number of gallons at some generic time t, well, it still matters how many gallons there were to begin with, so that's not going to change. I'm still going to need to start with the fact that there were 30 gallons in the tank, and I'm going to need to add however many gallons went in, but instead of between 0 and 3 this time, it's going to be between 0 and t. So my integral is going to go from 0 to t of the function 8. So over here, doing this work actually would help us set up part C a little bit easier. So originally I went from time 0 to time 3 of the function 8. So now I want to go from time 0 to some generic time t of the function 8. And now here's where I need to be a little careful. So notice I didn't write my limits of integration as t equals, because that wouldn't quite make sense to say from t equals 0 to t equals t of 8 dt. So in fact what I need is a dummy variable for my differential. So I'm just going to go ahead and call that x, because this is a of t, a function of t. So when I substitute in a number right here, I want that number to only be replacing this limit of integration up here. So I don't want it to have to do with the actual integrand or the differential. So I think maybe it'll be a little clearer in the next part. So this is how much water came in between 0 and t, and I need to subtract how much water fell out between 0 and t. So the leaking out function is this function here, g of t, which is radical t plus 1. So again, I don't want to put in that variable t, because that variable t corresponds to this a of t function that we're trying to write. So I'm going to call the dummy variable here x plus 1 dx. So let's try to think about it. We can make sure that our a of t function works by looking back at part b. So I should be able to substitute in a 3 right here and get the same answer I got in part b to tell me the total number of gallons at time 3. So plugging in a 3 right here for t means I'd plug in a 3 right here for t. So the integral from 0 to 3 of 8 would give me 24, just like it did over here. And then the integral from 0 to 3 of this function, radical x plus 1 dx, and it would give me the same value that I got from part A, this numerical value here. So again, I wouldn't want to put a t right here, because then it would look like I should take that 3 and put it right here, when that's not the case. The 3 is just the upper limit of integration, or the generic t. So this here is my expanded answer for the expression of a of t. Alright, and now the last part, part D. At what time t, where t is between 0 and 20, and note that this is a closed interval, we have less than or equal to, less than or equal to, is the amount of water in the tank a maximum? So at what time t is the amount of water in the tank a maximum? So let's look at this a of t function from the previous part, from part C. The amount of water in the tank at any time t is given by this function. So the units of this function are in gallons. So if I were to plug in again, so that number 3, into this function, I would get a numerical value, and that value would be the number of gallons in the tank after 3 minutes have passed. So this a of t is the amount of water in the tank. So I'll abbreviate that, the amount of water, H2O. So that's what this a of t represents. So at what time t is the amount of water in the tank? This whole thing right here is a of t. So this question is asking us, at what time t does a of t have a maximum? So to find a maximum value of a function on a closed interval, I have to check the endpoints and the critical points. So in other words, I am going to need a of 0, I'm going to need a of 120, and then I'm also going to need a of the critical points. So I'm going to need to find all of these values. So the way to find critical points is to set the derivative equal to 0 or undefined. So I have to find the derivative. I need a prime of t. And to find a prime of t, we're using the FTC part 2, because each of these portions here are accumulation functions. So the derivative of 30, well, that's 0. If I take the derivative of this function here with respect to t, because I'm finding a prime of t, so imagine like slipping in a little ddt right here. Since this is t and this is t, so remember what happens, we take this variable and we substitute it into the x that's here, but there is no x. So the derivative of this would just be 8, because there is no t to plug it into, so it would just be the function 8. So 8 is the derivative of this accumulation function. And now I have to take the derivative of this one, so imagine again sneaking a little ddt in here, so the t's match, this t goes into this x, so it would be minus the square root of t plus 1. So a prime of t is 8 minus the square root of t plus 1. So now I need to set that equal to 0. So 8 minus radical t plus 1 equals 0. So if we subtract the 8, and then divide by the negative, so both of these become positive. So in order to get rid of the radical, I'm going to square both sides. So I'm going to get t plus 1 equals 64. So I'm squaring both sides now. And so if I subtract the 1, t equals 63. And the units of this are going to be in minutes because it's a t, a time, and my time is in minutes. So in other words, I also need to check a of 63. So now it's a matter of substituting in these numbers into this a of t function and then determining what is the biggest value. So a of 0 is going to be 30 plus the integral from 0 to 0 of 8 dx minus the integral from 0 to 0 of radical x plus 1 dx. So that one's nice. 0 to 0, 0 to 0. These two integrals are 0, so the answer is 30 gallons. And then we need to substitute in a of 120 and a of 63. So we have 30 and then the integral from 0 to 120 of 8 dx, and then minus the integral from 0 to 120 of radical x plus 1 dx. And then we're going to have to do 30 plus the integral from 0 to 63 of 8 dx minus the integral from 0 to 63 of radical x plus 1 dx. Alright, so let's go ahead and see how this is going to turn out. I'm going to have to make some space, so I'm going to erase this. Alright, so this part would be, let's see, 30 plus, I'm doing a little bit of stuff quickly here. So this would be, the antiderivative is 8t, so when I substitute in 120 and then 0, it's just going to be 8 times 120. And we actually did this antiderivative earlier. It required a u substitution. And what ended up happening, so again, I'm doing some shortcuts. This was 2/3, and my new limit of integration, if I let u be x plus 1 to this 120, would be 121. So this is 121 to the 3/2 minus 2/3 1 to the 3/2. And then here, this would be 30 plus 8 times 63 minus, and then we have 2/3, 63 would become 64 to the 3/2, and then minus 2/3 1 to the 3/2. So we have to figure out what's biggest. Alright, so a lot of algebra later, we would determine that this is the largest number, so this is the amount of water in the tank that is a maximum, but then we have to be really careful. It says at what time t is the amount of water in the tank a maximum. So this was the biggest output value, but the answer is the time. So when did that happen? At 63 minutes. So that would be our answer. At 63 minutes, the amount of water was a max. So the justification is the work in showing how to find absolute maximums. And so, clearly part D is a lot more work, and oftentimes the latter parts of the problem are the ones that are going to be a little bit trickier than the previous parts. But either trying to get you to see that you could use the integration that you used from part A with a little bit of tweaking, and then this would be some simplifying, so I'd have to do the square root of 121, which is 11 cubed, and multiply that by 2/3, so we could see that this is actually a pretty big number when subtracted from 960, and that's why this one ends up being the bigger one. So a little bit of simplifying. You don't need to get it down to an exact whole number or a final answer, but it's justifying to yourself which one is bigger. So it's definitely between the second two, as opposed to a of 0, which is just 30. So once you decided which one it was, then the answer is either 120 minutes or 63 minutes. It's the time, at what time t. Alright, moving on to the next AP question. For times t between 0 and 31, the rate of change of the number of mosquitoes on tropical island at time t days is modeled by r of t equals 5 radical t cosine of t over 5 mosquitoes per day. There are 1,000 mosquitoes on tropical island at time t equals 0. So that this last sentence here says at the beginning, at time t equals 0, there were 1,000 mosquitoes. But then the rate of change of mosquitoes varies based on this function r of t. So the rate of change of mosquitoes is given by 5 radical t cosine of t over 5. So the units, because this is a rate, are in mosquitoes per day. So even though this is called r of t, I've been given a derivative. I've been given a rate of change, the rate of change of mosquitoes. So now let's look at part A. Show that the number of mosquitoes is increasing at time t equals 6. So I want to show the number of mosquitoes is increasing. So what I would need to show is that the rate of change of the number of mosquitoes is positive. So here's where a lot of students are going to make a mistake, is they're going to think I need to take the derivative of r of t and substitute in 6. Because they understand that to find where a function is increasing, I need to know that its derivative is positive. So at this specific time, I would need to show that the derivative is positive. But this is a derivative. This is a rate of change. It's the rate of change of mosquitoes. So if we want to show that the number of mosquitoes is increasing, I need only plug 6 into r of t and show that r of 6 is positive. So for part A, I need to find r of 6 and show that this quantity or this value is positive. So now going to our graphing calculator, we're going to use this function often, so we're going to store it as y1. This whole problem is a graphing calculator problem. So I've stored it as 5 radical x cosine of x over 5, again making sure I'm in radian mode still. When you enter this function, just be careful that the square root function stops with just x underneath it, and then you move to the right and get out of the radical before you put cosine x over 5. So the biggest mistakes are going to happen just entering in the function incorrectly. So now that this function is stored, I need to find r of 6. Well, we just called that function y1. So on the home screen, I'm going to go to vars, yvars, enter, enter to get y1. So what I want is y1 of 6, because we stored r as y1. So this looks exactly like this does because we stored r as y1. So now we can just go ahead and hit enter, and we get out 4.4379, etc. So this is a positive quantity. So r prime of 6 equals 4.437, which is greater than 0. So the number of mosquitoes is increasing. I'll just abbreviate mosquitoes, is increasing. So here the big picture is we don't need to see the prime notation to understand this is a derivative. The fact that this is a rate of change, mosquitoes per day, so this just goes back to the very first topic, the beginning of the year, understanding a quantity versus a rate. So since when substituting in a time here, I get out a rate, mosquitoes per day, this represents a derivative. So it's the rate of change of mosquitoes. So if I want to know whether the number of mosquitoes is increasing at time 6, I need only plug 6 into the rate of change of mosquitoes, which is called r of t. Alright, part B. At time t equals 6, is the number of mosquitoes increasing at an increasing rate, or is the number of mosquitoes increasing at a decreasing rate? Give a reason for your answer. Alright, so part B really pushes whether or not you understand, again, the concept of rates. So we just said that even though this has no prime notation, this r of t function is a derivative. It represents a rate of change with the units in mosquitoes per day. So substituting in 6, r of 6 was 4.437, but again, the units would be mosquitoes per day. So on day 6, the rate of change is 4.437 mosquitoes every day. Now, part B is asking, is the number of mosquitoes increasing at an increasing rate? So what that means is, we're trying to figure out if from day to day, the number of mosquitoes, the rate of change of the number of mosquitoes is on its way up or on its way down. So around 6, so on day 5 to day 7, on day 5 was the rate of change, let's say, less, and on day 7 was the rate of change more, so that the rate of change was on its way up, meaning that the rate of change was increasing at an increasing rate. Or maybe on day 6, the rate of change was 4.437, but on day 7, the rate of change was 2.437. So the rate of change is increasing. The number of mosquitoes on the island is still getting bigger, but it's getting bigger at a decreasing rate. So, in other words, from one day to the next, more mosquitoes are still going onto the island, but not as quickly. So either the number of mosquitoes we're adding is going up every day, or the number of mosquitoes we're adding is going down every day. That's the question we're asking. So in order to determine that, we are now going to need the derivative of the derivative. So we are going to need r prime of t's sign, whether that is positive or negative. So for part B, I'm interested in r prime of 6. That's a rate of change of a rate of change. So r prime of 6 is truly a second derivative. So to find r prime of 6, I can go back to my calculator. I still have it stored r as y1. So now I need a derivative. So math 8. And I have d dx of the stored function y1. And I want that evaluated at 6. So since this is a negative quantity, r prime of 6 is negative 1.913, which is less than 0. So the number of mosquitoes is increasing at a decreasing rate. So every day, more mosquitoes are going to be on the island, but the number of mosquitoes added every day is going to be less and less. So on day 7, maybe 4.2 mosquitoes are added, and then on day 8, 4.3 mosquitoes are added. So it's specifically, though, at time t equals 6. So we're interested in what's going on right at this time. So that's why we needed to calculate r prime of 6. So the answer is increasing at a decreasing rate. And that's the reason for my answer. So there's no explanation. The reason is the notation that we wrote down, that r prime of 6 is negative 1.913, which is less than 0. Alright, moving on to part C. According to the model, how many mosquitoes will be on the island at time t equals 31? So after the 31st day, how many mosquitoes will be on the island? Round your answer to the nearest whole number. Alright, so here on this problem, we are going to need to take into account 1,000 mosquitoes, which is how many were on the island to begin with at time 0. So for part C, how many mosquitoes were on the island after 31 days? So 1,000 is where we were to begin with. And now r of t is the rate of change of the number of mosquitoes at different times t. So I'm going to need to integrate this quantity. So I'm going to add the integral of the rate of change between 0 and 31 days. So between t equals 0 and t equals 31 of r of t dt, this is the net change in the number of mosquitoes. So this is the total net changes in how many were added, how many were subtracted over the whole course of 0 to 31 days. So this is the total net change plus how many there were to begin with. So now this can be evaluated in my graphing calculator. And again, if you don't understand why just outright this represents the net change in the number of mosquitoes, we can always go back to units. So again, just graphing R of t is some generic function where the units of R of t are the rate mosquitoes per day. After so many days, t, the area, again, the units would cancel. Area is base times height, so mosquitoes per day times days. The units of days cancel to give us just mosquitoes. And my answer, or my question, was asking for how many mosquitoes. So we're plugging this into our calculator. R of t has been stored for a while now, so we're going to do, and if we want, we could jump straight to 1,000. Whoops, let's do that. So let's say 1,000 plus, and then math 9, the integral from 0 to 31, and then our function is y1, and the variable is x. So this up here means it's taking a little bit of time to compute. So our answer is 964. So let's go ahead and write that down as our answer. And again, we were allowed to round our answer to the nearest whole number because there's no such thing as, 1/3-ish of a mosquito. So we could just say 964 mosquitoes is our answer. So it turns out that over the 31 days, the rate of change of the number of mosquitoes told us that a lot of them were dying out, right? So we started out at 1,000 and we added the net change in the number and we lost 36. So that's what happened during the time frame from 0 to 31 days. And finally, part D. To the nearest whole number, what is the maximum number of mosquitoes for times t between 0 days and 31 days? Show the analysis that leads to your conclusion. So trying to figure out what was the maximum number of mosquitoes at a particular time on the island. What was the most amount there ever was? So we know how many mosquitoes there were on the island at time 0 to begin with. So this is a closed interval, so I would need to determine how many there were at time 0. Now here's the biggest mistake students are going to make is they're going to say that we're trying to maximize R. So they're going to say, well, we want R of 0, we want R of 31, and then any critical points. So set this R equal to 0 to find the critical points. But that's not the case. We're not trying to maximize R. So I'm going to erase this because this is completely wrong. So we're not trying to maximize R. R is the rate of change of mosquitoes per day. I want to maximize the mosquitoes per day. So I don't have the name of that function. So we're used to using that notation. We want to maximize f, so we set f prime equal to 0, etc. But we don't need that notation in order to figure out all the important days that we're going to need to check. So all we need to do is say that at t equals 0 days, there was 1,000 mosquitoes. And we even have how many mosquitoes there were at 31 days. We solved that in part C. So at 31 days, there was 964 mosquitoes. So right now, just checking the endpoints, we know that, or we could say that the current maximum would be 1,000 mosquitoes. But we need to check any critical points. So we need to check critical points by setting the derivative equal to 0. And again, for the who knows how many times, this is the derivative of the function that counts mosquitoes. So we don't know what that function is. We don't have a name for it. But the derivative of that function that counts the number of mosquitoes, the rate of change of the number of mosquitoes, is R of t. So I need to set this derivative equal to 0. So how we're going to do that, because we have a graphing calculator, so ultimately this is what we're trying to do, figure out when does R of t equal 0, between 0 and 31, we're going to graph it. And we already have it stored, so here's our y1. And before we graph it though, I'm going to go ahead and modify the window. So x min, so x in this case represented our t. And we only care about what's going on between t's between 0 and 31. So our x min will change to 0, and our x max will change to 31. All right, so now our y min. So y being the output. So here, let's just go ahead and leave negative 10 to 10, because we're not entirely sure what this function maybe is necessarily going to look like. I mean, it has the cosine function in it. Just cosine itself goes from negative 1 to 1, but just to see, let's go ahead and graph this function. All right, so we have a pretty good picture. We don't have the entire picture, but we do have where r of t equals 0 clearly shown. So there's two places where this function r of t equals 0, this derivative equals 0. So we have two critical points right about here and right about here. Now, normally we would have to check both critical points, but we are trying to find the maximum number. So I would say that the best thing to do is to eliminate any minimum, local minimum value, because that's not potentially ever going to be a maximum. So here this derivative graph changes from positive to negative, so that means the original function goes from increasing to decreasing, so this point here would be a local max. This is the one we want to keep and we care about. This other function, or this other critical value, critical point, is going to yield a local minimum because this derivative graph changes from negative to positive, making the function change from decreasing to increasing, the original function, which means there'd be a local minimum. So we do not have to care about this point, only this one. Alright, so now I have to find this 0. So to review how to find zeros on our calculator exactly, because let me point one thing out, the trace option doesn't work. So here's what I absolutely cannot do is just move my arrow over and get kind of close to that point and say, oh, that's the x value that I need. I absolutely cannot do that and will never ever work. So I have to go to second trace for calculate, 2 for 0, and now it's asking me for the left bound. So I want to be to the left side of this x-intercept right here. So I want to move to the left. So now I'm clearly to the left of this x-intercept. So I don't want to think about it as above or below the graph, the x-axis. I want to think about it to the left or to the right. So left bound, yes, so I hit enter. Right bound, now it's telling me get to the right side, which in this case would be down here. I'm on the right side of this x-intercept, so I hit enter. When it says guess, we always just hit enter. So now we have that this 0 is 7.85398, etc. All right, so if we want to remember that value, we could go ahead and write it down. So 7.853. So let's just write it down so we remember it. But here is something that is crucial. I cannot just take this value, even if you go out to 25 decimal places or 25 places past the decimal, I cannot just take this numerical value and type it in right now when we set up our integral. I have to store this value. So right now the calculator is holding this number as your last answer. So what we're going to do, as soon as you see this value as the 0, I'm going to go to second and quit. I'm going to get to the home screen. And the first thing I'm going to do, I can't touch anything else, I have to hit STO for store. So what the calculator is doing is it's storing your last answer, which was they're only saving the x coordinate. So the last answer, I want to store it to any letter in my calculator except x. I don't ever want to do that. But I want to store it to, let's say, A. So alpha A. So I'm using the green buttons on the back. If you have a different color calculator, it might be a different color. So alpha and then any letter you want. Usually we pick A, it's closest, and then we hit enter. And then we wrote it down so we remember. A is now 7.853, and it's the exact answer with all of the decimal places stored. So now I want to keep and hold that number. So that answer is in terms of days. days. So potentially the maximum number of mosquitoes happens at 7.853 days. The only way we're going to know is to evaluate the integral from 0 to a. So what I'm going to do is, instead of calling this t now, I have labeled it as a. And on the AP exam, you're going to want to do this as well. So you're going to want to list what you stored as a, and then the integral we're setting up to find the number of mosquitoes there were at 7.853 days is the integral from 0 to a of r of t dt. So now we're going to go to Math 9 for integrals. 0 to my upper limit of integration is now a. So under no circumstances can you type in just 7.853. Or even 7.853 blah 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 1020 places past the decimal. You have to put the stored value in. And then we can go ahead and choose the function y1 again, and then dx, and enter. And this number is going to represent the net change in the number of mosquitoes between 0 and 7.853 days. So this is the net change in mosquitoes between 0 and 31 days. So we can't forget to add, didn't leave much space for it, but we can't forget to add 1,000 to that net change. So that's how many mosquitoes were added to the island between 0 and 7.853 days. But there were already 1,000 to begin with, and our question's asking what's the maximum number there were. So the answer here is 1,039 mosquitoes. So the nearest whole number, we're rounding again, and that would be the maximum. So what is the maximum number of mosquitoes? 1,039 mosquitoes. And now to the final AP question we're going to take a look at. A tank contains 125 gallons of heating oil at time t equals 0. During the time interval t between 0 and 12 hours, heating oil is pumped into the tank at the rate of h of t equals 2 plus 10 over 1 plus natural log of t plus 1 gallons per hour. And during the same time interval, heating oil is removed from the tank at the rate of r of t. So 12 sine of t squared over 47 gallons per hour. So before we look at the parts of the question, let's make sure we understand what's happening. We have this tank that starts out with, at time 0, 125 gallons of heating oil. And between 0 and 12 hours, oil is pumping into the tank at this rate here in gallons per hour. But during the same time interval, heating oil is also being removed from the tank at this rate of 12 sine of t squared over 47 gallons per hour. So this is a calculator problem, and we're first going to enter in each of these functions as y1 and y2. So we'll go ahead and enter 2 plus. Now when I have a rational function like this, I want to make sure and enter the numerator and denominator in their own set of parentheses, especially if I don't have this updated calculator. If you have the updated calculator, we could always go to alpha and then y equals and choose 1 for numerator over denominator, and then just enter in the rational or the function exactly as it looks. So we have 1 plus natural log of 1 plus t, or t x in this case. The order doesn't matter there. So I entered 1 plus x, that's the same as x plus 1. And then we'll go ahead and enter in our second function. So that one is 12 sine of the quantity. So we have t squared, so x squared, get out of the exponent, and then divide by 47. Alright, so we want to make sure we've entered in our functions correctly, because we're just going to now use the stored versions of y1 and y2 every time. We also want to keep straight the order that we entered them in. So because h of t came first, that one's y1, and I want to remember that, and then r of t is y2. Alright, so now that those are stored, let's go back and answer the questions. So for part A, how many gallons of heating oil are pumped into the tank during the time interval from 0 to 12 hours. So in this part of the problem, we're asked to find how many gallons. So I have my functions in gallons per hour. So I know I'm going to have to integrate these functions in order for the units to cancel out. We've done that a few times now. The units of hours will need to cancel, and then we'll have our answer in gallons. So we know we're going to need to do some integrating here. So we're going to need to integrate the function that involves pumping water into the tank. So how many gallons are pumped into the tank? So that was h of t between 0 and 12. So the integral I'm setting up is the integral from time 0 to time 12 of h of t dt. So it's just how many gallons were pumped into the tank, not how many gallons are in there total, so we don't have to care how many there were to begin with. It's just how many were pumped into the tank between 0 and 12 hours. So now h of t was stored as y1, so in case we might tend to forget, we can always label them as well. So they're stored for us. We can go to the home screen. We can go to Math 9 to set up our integral from 0 to 12, 12, of h of t, which we stored as y1. So vars, y vars, enter, enter, dx. And the answer is then 70. And because we were not told to round, we would always go to at least the thousandths place. So either round or truncate. So I'm going to write 570. And I also write the other answer that would be accepted on the AP exam, 70.571. So rounding the 10,000ths place over 1 because that value was bigger than 5. So we would get 571 thousandths or 570 thousandths. So these two would be the acceptable answer for part A. Now, you cannot just write the numerical answer for my test or for the AP exam. The points are for the setup, for the limits of integration, for the integrand. Now, you don't actually have to go through the process of writing out h of t, which has already been given to us. You can just go ahead and call it by the name it was given, h of t. So there would be a point here for the limits of integration, a point for the integrand, and a point for the numerical answer. But just putting the numerical answer doesn't get you anything. So now, for part B, is the level of heating oil in the tank rising or falling at time t equals 6 hours? Give a reason for your answer. Alright, so we have this tank that's filled with oil, so we don't know the shape, but let's just say it's like a cylindrical tank. It has 125 to begin with. So at time 6, we're trying to figure out, is the level of the heating oil rising or falling? So the level has a measurement, let's call it H. So we want to know if more oil is coming in than is falling out. So if more oil is coming in at 6 hours, then is coming out right at 6 hours, then the level would be rising, the level of the oil. But if more oil is falling out right at 6 hours than is coming in, then the level of oil would be falling. So we're comparing rates here, the rate at which oil is coming in and the rate at which oil is coming out. Which one's sort of winning the race? So here we're comparing H of 6 and R of 6. So H of 6, the rate at which oil is coming in, is a value we can find on our calculator exactly. So H was Y1, so Y bars. Y1 of 6 is 5.394. So 5.394. So this is in gallons per hour. So this is the rate at 6 hours at which oil is coming in. So now let's compare that to R of 6. So that would be vars, Y vars. We can go down one to Y2 of 6. So the rate of oil coming out is bigger. It's 8.3 318 gallons per hour. So since more oil is coming out than is going in, the level of heating oil must be falling. So a reason for my answer is because R of 6 is greater than H of 6, the oil level is falling. And that's all we would need to state. So this portion here is our justification because 8 is more gallons per hour coming out than 5, which is the gallons per hour that are coming in right at 6 hours. Moving on to part C. How many gallons of heating oil are in the tank at time t equals 12 hours? So at 12 hours, how many total gallons are in the tank? So this is where we're going to have to take into account how many there were to begin with. So at time 0 to begin with, there were 125 gallons. So 125 plus, well, I need to figure out how many entered between 0 and 12 hours. So how many entered is going to be the integral from 0 to 12 of h of t dt. And that answer was also found in part A. So how many gallons of heating oil are pumped into the tank between 0 and 12 hours? That answer was found in part A. So how many total gallons are in the tank at 12 hours? Well, 125 was what we had to start with, plus this is my setup from part A. This is how many gallons entered during the 12-hour time frame, and I need to subtract how many left. So heating oil was removed based on the second function r of t. So between 0 and 12 hours of the r of t function will tell us the net change of how much oil came out between 0 and 12 hours. So what I had to begin with plus what went in minus what came out is going to give me the total amount of oil in the tank at time 12 hours. And it's going to take our calculator a bit of time to compute this, but I do want to enter this in as one giant expression. So I wouldn't want to find this answer or use my answer from part A and then calculate this and then subtract decimals and really ultimately get a worse off approximation. So in other words, I don't want to ever approximate intermediate steps, because if I were to truncate this at 3 decimal places and then truncate this at 3 decimal places and then go through the process of combining all of these, that's not going to give me as exact an answer as entering them all in at once. Alright, so I've entered in all of the values and I ended up with 122.025. So we could now round this final answer, so you'll see all of the integrals are entered there, as 122.025 or 122.026. Those would be the two acceptable answers. My units would be in gallons. So how many gallons were in the tank at 12 hours? So 122. So originally we had 125, so over the time frame it seems like definitely more came out than came in, because we ended up with less than we started out with. And finally, part D, and this is one of the trickiest parts of really any problem that involves this concept of one function that has something coming into an object and then another function that takes away. So this is going to be a little bit intensive on the graphing calculator and a little bit intensive to understand. So at what time t, for t between 0 and 12 hours, is the volume of heating oil in the tank the least? Show the analysis that leads to your conclusion. So I'm figuring out what time the volume, or really the quantity of heating oil in the tank, is the least possible amount. So I'm trying to minimize the volume of the heating oil. Now, right now, what I have in terms of functions is the rate of change of oil entering and the rate of change of oil leaving. So I don't have a function right now that represents the total amount of oil in the tank at any particular time. But I'm pretty much going to have to write one. So I'm going to call that function v of t, so for the volume of oil in the tank. And I'm going to, once I write this volume function, I'm going to try to minimize it. I'm going to try to find the absolute minimum value, the least quantity, between 0 and 12 hours. So the volume at any particular time, and hopefully this will seem familiar after you've done it enough times, the only thing that changes in these problems is what's coming in and what's going out. So the total volume is 125 gallons, what you had to begin with, plus the integral from 0 to some generic time t of h, and I can't call it t again, so let's say h of x dx. So let's stop and think about this. It's what we had to begin with plus how much is going in between 0 and t minus how much is going out between 0 and t. So we'll have to say that that is now r of x dx. So this function v is now representative of the total amount of heating oil in the tank at any time t. So the units of this function are in gallons. And in order to find the minimum, we're going to need to check the endpoints and the critical points. So the endpoints are 0 and 12. So we need v of 0, the amount of oil in the tank at time 0. We're going to need v of 12. Well, thankfully, we have those values. At time 0, there was 125 gallons. At time 12, we just did that in part C. So that was 122 gallons. 122.025 gallons. So now it's a matter of finding critical points, which means taking the derivative of this volume function that we're trying to minimize. So we need v prime of t. So the derivative of 125 is 0. The derivative of this integral with an upper limit of integration of t, so we're taking ddt of the integral from 0 to t, which is just taking this t and substituting it into this x. So v prime of t is h of t. And then taking the derivative of this function here, again, same thing. T goes into the x. I'm taking the derivative with respect to t. This is an accumulation function. This is an application of the FTC part 2. So minus r of t. So what I want is where the derivative equals 0. So I need to know, when does h of t minus r of t equal 0? So now let me remind you that we stored h of t as y1 and r of t as y2. So what this amounts to is, when does y1 minus y2 equal 0? Well, there's kind of a cool thing we can do on our calculator. We can, since we have already stored y1 and y2, we can go down to y3, and while we absolutely could retype out this function, h of t, and this function, which was r of t, what would make it even quicker is if we just entered y1 minus y2 as y3. So now y3 is y1 minus y2. But when I graph this right now, I don't want to see y1 and y2. I don't want to delete them. I can't delete them because y3 is referencing y1 and y2. But what we're going to do is hover over the equal sign and hit enter to turn it off. And all that means is I don't want to see it when I graph right now. It doesn't mean I want to get rid of it altogether. So again, don't delete y1 and y2, just turn them off. And we're going to change our window from 0 to 12. So that those are our t values that we care about here. And we can leave our y min, y max for now until we potentially have to change it. So this function that's being graphed can be thought of as v prime of t. Now remember, we're trying to find the least amount. So we're trying to find a minimum. So on this graph, this is a derivative. If the derivative changes from positive to negative, the original function goes from increasing to decreasing. That's a maximum. So in other words, I do not care about this critical point right here. I do, however, care about this one because the derivative that is graphed is changing from negative to positive, so this is a minimum. Alright, so I skipped showing finding the 0 on my calculator, the process that we did earlier. So I found the 0 of this critical value that I care about, and the 0 was 11.318. So I do want to write that value down before I store it. So I'm going to go ahead and just write in the corner A, because that's what I'm going to store it as, is 11.318. So now let's remember, we go to second quit immediately, hit store immediately, and then choose a letter. So if I choose A, I have to know I'm rewriting over the other A that I stored. So now A is this 11.318 value. So that's the critical point. So now the other quantity that I need is V of A. I'll go ahead and call it. Since I wrote A over here, I can just write A as what I'm evaluating the function V as. So V of A is 125 plus the integral from 0 to A of h of t dt minus the integral from 0 to A of r of t dt. Sorry, ran out of space there. But how we calculate this is how we calculated the time 12 hours in part C. We enter the whole thing into the graphing calculator all at once. Just to show you another kind of cool thing we can do, these two integrals, by our properties of definite integrals, can be thought of as the integral from 0 to A of h of t minus r of t. Well, we called that in our calculator y3. So I'm saying that so that right now when I enter in my integral, it'll be a little bit faster to say plus, and then math 9, the integral from 0 to A of y vars, and then y3. So y3 was y2, or y1 minus y2. So I can do that instead. Which is going to take the calculator just a couple seconds longer because now it has to reference some other functions, but definitely not too long. So that means that 120.738 is my answer to V of A. So the minimum value, that's right, 120.738, doesn't look like a 3, 738, is the smallest. So at what time t is the volume of heating oil in the tank the least? Show the analysis. This is showing the analysis, checking V of 0, V of 12, and V of A, and you are going to have to specify what A was and that you checked it, because in fact that A ends up being the answer. So at what time t? At time 11.318, what were my units? Hours. This is the minimum. So this is the justification, and ultimately this is my answer. So sorry we kind of ran out of space on that last one. But part D typically does have the most amount of work and is the most challenging. What I will leave you with is that hopefully you started to see some of the patterns in these problems. They are not always going to be identical. They're not going to have the same structure. They are going to require you to definitely understand what a rate is, understand the concept of units, what happens when we take the derivative, what happens when we take the integral, what happens when we just substitute in values into the functions that we're given. There's a lot of conceptual understanding here. And there's also a lot of applications to the graphing calculator. So we've definitely gone through a roller coaster with not being able to use our calculator at all for a big portion of this class, but now you need it, and you need to know the ins and outs of your calculator. It's not optional to not know how to store these functions, not know how to find zeros, store the limits of integration. You have to know how to do this to be able to get these questions correct on the test that's coming up. So if you have a different calculator and you want to work one-on-one with it, you're going to have to come in long before the test to get help with it, because it is something that requires some practice and some getting used to, and you don't want your calculator to get stuck on you during the test, or I can't answer those questions during the test. I can't tell you how to clear it or how to clear the memory, or if it's in radian mode or degree mode and your answers are all incorrect. Those are things you have to figure out long before you take the test. So hopefully you definitely got to the end of this video, because this part D is the most important one, especially that it has two functions associated with it. So you will absolutely see this type of problem all over the assessments that you'll take going into the near future.